So I am Joyce Penner, and I am the outgoing president of the Atmospheric Sciences section. We're going to do this in a little bit strange order because we have our Atmospheric Sciences luncheon about a 15-minute walk away. So I'm going to introduce Paul, give him our certificate, and then you'll hear the lecture, and Jim will handle the questions while I duck out. But our 2018 Jewel Charney Lecture is awarded to Paul Newman. Paul completed his doctorate in physics at the Iowa State University. And then afterwards, he was a National Research Council Fellow. He also worked at the Applied Research Corporation from '86 to '89, and the University Space Research Associates from '89 to '90, and he's currently working at NASA since 1990. His principal area of research is stratospheric dynamics and chemistry. He's participated in numerous aircraft field campaigns with NASA, NOAA, and university colleagues, and actively researches dynamical and chemical processes. Moreover, he is currently the co-chair of the Scientific Assessment Panel for the Montreal Protocol, which is charged with drafting reports on the state of ozone depletion every 4 years. So please help me welcome Paul as our 2018 Charney Lecturer. And you get this. Now you have to lecture.
Thank you, Joyce. It's a real honor to be giving this talk, particularly since it's the Jewel Charney talk. As many of you know, Charney was one of the real founding fathers for numerical weather prediction. And in this talk, what I'm going to do is I'm going to make a pretty bold assertion, certainly it will get me in trouble at NASA, that in fact, Earth sciences is perhaps the greatest achievement that NASA has ever done. And I say that thank you, Faye. The moon landing and the landing of, for example, InSight on Mars are fantastic achievements. And I'm immensely proud to be part of the organization that's done that. But I think if you reflect for a minute or two about what really impacts your daily life, you will realize that Earth science has made spectacular contributions, and in particular, the satellites that we use every day, nonstop, 24/7, 365 days a year. In fact, a constellation of satellites gives us things that are unbelievable. And I think most Americans, most people in the world have no idea what they get on a daily basis from satellites that are in orbit. So it's NASA's 60th anniversary, and I'll talk about anniversaries a lot. In particular, the AGU was established in December 1919. This is why it's our centennial this coming year, and you'll hear a lot about that. But it's a real honor to kind of kick this off, and to kick it off because Charney is I think, the dream that he had of numerical weather prediction. I believe that we've achieved that. I mean, we really do a fantastic job, not only in long-term projections, although that's rejected by many in this particular town, We do those things. We do seasonal predictions. We do terrific. When I was a kid, you know, weather forecasts were astonishingly bad compared to what we have today. And so I think it's a real achievement. So just before I jump to that, I say atmospheric chemistry from space, past, present, and future. When I really got into this, I found about 2 weeks ago that I had over 200 slides in this presentation. Don't get nervous, that's been cut down. But also, the topic is pretty broad. And that was because I think Joyce called me up the morning after a previous late night adventure. And so I was a little bit too optimistic about what I'm going to talk to. So what I'm going to really talk to is about atmospheric ozone in particular. So you'll see a lot of ozone charts. You'll see a few other things. But also I'm going to keep it sort of on a NASA ozone level. So then I go to the next slide here. And I'm going to talk about the convergence of satellites and NASA with ozone science. And I'm going to address a few questions. And I hope you'll see this as we go along. And I hope you'll come to agree with my assertion that Earth science is perhaps the greatest achievement that we've made here. So how did we get, and I'll start off with how do we get from V2 rockets to NASA Earth science? That'll be one fundamental thing that flows through this. And how is ozone science convolved with NASA? So why is NASA so heavily involved with ozone research? And how did the ozone issue itself evolve in time? And so what do we see as the trajectory of ozone science and related research? And there's actually two aspects to this. What do we see the trajectory of ozone on our planet, but also what do we see as the trajectory of policy in the future? So I'm going to talk about the past first. And I'll start off with a paper that was made by Gordon Dobson in 1926, so 7 years after the foundation of AGU. And in this paper, he demonstrated that low ozone was related to anticyclonic systems and that high ozone was found co-located with cyclonic systems. And so back in those days, they weren't quite sure, was ozone driving weather systems or vice versa? It was not really understood at that time, but they knew this was true. So this is a very important paper early on. People are figuring out that ozone and somehow weather are related to one another. So I'm going to jump forward a little bit. I'm going to have to skip a lot of steps along here just in the interest of time because you don't want me to show the 200-slide presentation. On October 24th, after the end of the Second World War, the United States brought about 200 V2 rockets to White Sands. Now, V2 rockets, these were German weapons of war. They were rained down on cities like London. They were a terrible thing. But in fact, this was the foundation for some of the early rocketry research. This is the first picture. It was captured from a V2 rocket launch from White Sands back in 1946. And there were a number of these other little achievements. I mean, we take for granted telemetry and things like that, communications, Earth locations, but in fact, it was these launches of these rockets that actually led to all of these things that are really fundamental to satellite systems nowadays. And so that was developed very early on. So taking, the old adage about taking our swords and spears and beating them into plowshares, this is exactly how this evolved back in the 40s and early 50s. So then I'm going to jump to another thing, the International Geophysical Year. And in fact, on the 5th of April, about 8 miles north of here in Silver Spring, the house is still there, James Van Allen, he hosted a party, a dinner party with Lloyd Berkner, who was really the executive secretary for U.S. research. Sidney Chapman was the ozone scientist who actually figured out the photochemical balance of production in the upper stratosphere with odd oxygen loss processes. So he figured out how the ozone profile actually was theoretically formed. Wallace Joyce, Ernest Vestine, and a person who's very familiar to us, many of us, S. Fred Singer. S. Fred has quite a reputation now, but he's actually, you find his name littered all across this early ideas of the International Geophysical Union and satellite development, instrument development for satellites. And I'll probably mention him again as we go along. So at this dinner party, Berkner and Chapman conceived the idea of having another international polar year. And they decided, oh, 57, 58, that'll be the peak of the solar cycle. Why don't we do it then? So this was in 1950. And so in 58, they were going to have 57, 58, they'd have the IGY. So that evolved. They went to a couple of meetings at Caltech and Penn State. They took this to the US Mixed Commission on the Ionosphere, and then it went to ICSU. And ICSU decided maybe it should be more than just the International Geophysical Year. Maybe it should be, or not the International Polar Year, let's make it into the International Geophysical Year. So the idea evolved to be more global in scope, still with a very heavy polar emphasis. And then in July of 55, the White House, President Eisenhower issued a joint announcement with the National Academy and NSF that the US was going to build satellites for IGY. This is in 1955. So this is a big important step. I think many of us fail to recognize that we do our science because Congress or our particular country funds it, okay? It is important to get your science, explain why the country needs to do your science, and get somebody like an Eisenhower to say, yeah, let's go ahead and do that. Oh, one other thing. Let me go back. The top point about James Van Allen hosting this dinner party. We come to meetings like this and we show our science, but it's important to socialize. This is how science really evolves. It doesn't evolve in rooms like this. It involves out there in the corridors and at parties, and in my case, at bars. But you really need to socialize when you come to these movies. So just for all the young folks in here, keep that in mind. It's okay to go out with your buddies after the meeting. So I'm going to show a little movie here about Sputnik, because this is another key moment in the evolution of satellite. I like the Reds launch first space satellite.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket. Here, an artist's conception of how the feat was accomplished. A three-stage rocket. Number one, the booster in the class of an intercontinental missile. Its weight estimated at 50 tons. The smaller second stage took over at 5,000 miles an hour and carried on to the highest point reached. 500 miles up, the artificial moon is boosted to a speed counterbalancing the pull of gravity and released. You are hearing the actual signals transmitted by the Earth-circling satellite. One of the great scientific feats of the age.
Okay, so Sputnik set off a thunderclap here in the United States. The week after this video, Eisenhower got up in front of the press corps and explained that the United States was not behind in the space race. That we had satellites that were in preparation. And of course, that was followed in December of 1957 when the first Vanguard blew up on the launch pad. So there was a real, the US kind of was feeling it was behind in the space race. And so there were a few things that happened. The first thing as of course I explained, they accelerated this launch of a Vanguard. It blew up. That was bad. But they had Senate hearings, and this woman, Eileen Galloway, I believe is she is the mother of NASA. And I actually quote here what she organized hearings for Lyndon Johnson at the time, a Democratic senator. He became president, but he was a Democratic senator at that time. She organized the hearings. And you can see she's hearing the testimony of scientists and engineers. And the scientists and engineers were telling her that, in fact, these rockets, these satellites, can really advance our knowledge for the Earth. And so they decided that maybe we shouldn't, remember all of the rocketry was controlled by the military at that point. And they decided we should have a civilian space agency. And so Lyndon Johnson with Dwight D. Eisenhower decided to do that. They were going to, in fact, create a space agency. So they created NASA. This is the National Aeronautics and Space Act of 1958. And you can see in the very top line there, the policy of the United States that activities in space should be devoted to peaceful purposes for the benefit of all mankind. You go down and there's sub-bullets there. They talk about the expansion of human knowledge for the atmosphere and space, and the establishment of long-range studies for peaceful and scientific purposes. This is the NASA Charter. So this is still the act that created NASA and that we still pay attention to. Okay, so I have to go back to another movie reel because I really like these things. It's a lot of fun. You can go buy your own birthday movie reel from the National Archives. But this is getting to sort of the next stage. And this is about Vanguard 2.
We'll carry it aloft. This satellite's electric eyes will scan the Earth's cloud cover, broadcasting data never before attainable. The weather station's batteries will last only 2 weeks, but it will usher in a new era of global weather forecasting. A scientific triumph for the new civilian space agency, the launching is a vindication for the sleek three-stage Vanguard space vehicle. One of the most technically sophisticated of the space rockets, the misfortune-plagued Vanguard 6 times failed in widely publicized launching attempts, only once placed a 3-pound baby moon in orbit. But on this day, the Vanguard outdoes her designer's hopes. She soars aloft to join 4 other satellites still orbiting the Earth, 3 American, 1 Russian. Defense Department films show the perfect flight, mathematically flawless all the way, that carries the weather satellite into an orbit even farther out than hoped for, assuring a lifespan of decades, perhaps centuries, for America's eye in space.
Okay, so Vanguard 2. Now, Explorer 1 was the first US satellite that was successfully launched. That was a JPL mission. Vanguard 2 is the first weather satellite. So a lot of people believe it's Tyros 1. It was actually Vanguard 2, and it simply had a couple of photocells on it. And in fact, all of these engineers, these were originally people who were working on Vanguard, were from the Naval Research Lab here in Washington. And after the NASA was formed in 1958, they were simply moved to the Goddard Space Flight Center. So they became part of the earliest part, actually the foundation of Goddard. And they actually built, in case Vanguard 2 blew up, they had a backup, and the backup still exists. And there it is. This is actual Vanguard 2. It's been gutted. It's a magnesium sphere. It's about as big as a beach ball. You can see the antennas poking out of it. You can see the little gold photocell port there. And if you, right now it's corroding a little bit, sitting in a warehouse up at NASA, kind of like if you all remember Raiders of the Lost Ark, when they rolled the Ark of the Covenant into the warehouse. And if you go here, it's actually pretty interesting. You actually do see some very interesting stuff as you go along. So that brings us to Tyros 1. Tyros 1 was a tremendous achievement. Vanguard 2 only lasted 19 days because it simply ran on battery power. It didn't have any photocells on it, so it couldn't, it didn't have any solar arrays on it. So it literally just lasted as long as the nickel-cadmium batteries ran it. Tyros 1 was the first real successful weather satellite. And in fact, going back to Vanguard 2, actually Vanguard 2 is still in orbit. And it'll probably orbit for about 200 years before it actually comes down. So if there's ever a mission to space where we can retrieve it, that would actually be better than the backup copy. But so on to Tyros 1. So now, sort of the achievement of Jules Charney, they were actually using these weather images to help in weather forecasting. And so Tyros really gets the nod as the first really good weather satellite. Now that brings us to ozone. Now at the same time as Tyros was going on, there was another program, OGO, the Orbiting Geophysical Observatory. This is the 4th. And it had a little ultraviolet instrument. This was one that was built by Charlie Barth. You can see the picture of it there. You can see the OGO-4 launch picture down in the far left. And of course, up on the, this is the first paper on OGO-4 was this ozone retrieval that was done by Gail Anderson. And here you can see her profile. Here's the actual operations room. When you see the little video of the InSight landing with everybody and these big fancy, that's not what it used to look like. It was these men in black here and these very functional government rooms originally. So there's the first ozone profile from a satellite. So this was, and the reason they did this was because they were hoping, they were sort of the scientific objective of let's do some science on ozone, but they also were looking at ozone as a way of looking at weather. So it was weather related. And the third thing was you could actually build instruments pretty simply that measured ozone. They were looking for things they could do from space. So there's three rationales for why they were actually putting an ozone instrument onto OGO. Well, that takes us to the next thing, which I think is a critical moment in Earth science. And this is the picture from Apollo 8, and this is the famous, what we call the Earthrise picture. Now, I was a boy at that time, and this had a huge impact personally on me to see, and it wasn't so much that we were orbiting the moon, although that was a real triumph, to look back at this little blue ball floating in space with this just very, very thin thing we call our atmosphere here. You know, a few thousand kilometers in diameter, but the atmosphere being like 16 kilometers, up to 100 millibars, 16 kilometers in depth. You know, we sit on a very, very tiny thing. We think of the atmosphere as being huge, but it's not that big compared to the planet. It's just a veneer on top of a rock. And just to quote here from Jim Lovell, that the vast lowliness is awe-inspiring, but it makes you realize what you have back on Earth. And I think this did have a huge impact, I think, on it had some impact on the first Earth Day, so the Earth movement, just looking at our planet. So I'm going to take it back to ozone again here, and I'm going to show a picture of a couple of people who made some really critical discoveries. The first was here is Paul Crutzen. Paul came up with the Knox reaction of how you could actually cause ozone loss. So Knox actually results with a little bit, with a photon, can result in converting ozone into oxygen. Then there's the next thing that comes along. Here's Hal Johnson down here. He actually began to ask the question about what would, because of studies like this, what would SSTs, which were spewing out NOx from their tailpipes, what would they do to the ozone layer? And he did a series of simulations. You can see the bite outs from a large fleet of SSTs flying up in the stratosphere. And so that had a huge impact. Okay, so what might happen to ozone because of SSTs? So here's where you get the interaction of politics with the science. Congress authorized the Department of Transportation to investigate SSTs. And what they did is they formed a program at DOT, the Climate Impact Assessment Program, and they were going to look at a variety of problems. Ozone was one aspect of that. But it had over 500 scientists involved, $20 million in funding at that time, which was a lot more money back then than it is now. And SciAp actually established, it actually did the linkage between ozone depletion and skin cancer. Now, back in the 50s, they recognized that, in fact, the ozone layer was a shield against ultraviolet radiation. That was recognized back in the 50s. And in fact, that was one of the reasons they also wanted to study ozone back then. But that wasn't the primary motivation back then. SciAp really established this idea of ozone depletion and skin cancer are linked. So that brings us to the next topic, and kind of the evolution during the 70s of chlorofluorocarbons. And the first thing that you should note here is Jim Lovelock created the electron capture detector. And this allowed you to measure CFCs down at these part per trillion levels. It was a real key thing. And in 1970, in Ireland, Jim actually showed that CFC11 levels were pretty high because it's a purely man-made gas, and this CFC11 was accumulating in our atmosphere. So in 1971, there was a NASA report, and I'm showing it up here, remote measurements of pollution. And I got a couple of key phrases here. They talk about the photodissociation of chlorofluorocarbons here, that they would only be photolized in the high stratosphere. And the last phrase here is really the accumulation they talk about, but clearly this situation is cause for concern. And they're saying this in 1971. Lovelock went on and he made more measurements, showing the difference between the northern hemisphere, where you're producing all the CFCs, and the southern hemisphere, where it's being transported. And so he's showing that the CFCs are accumulating in our atmosphere. Now, I go to another one, and I've got a picture here. This is Rich Larsky over here on the left, and on the right is Ralph Cicerone, recently passed away, Ralph. But they published a paper on stratospheric chlorine, a possible sink for ozone. And so they showed that, in fact, chlorine could, if it was increasing, deplete ozone. Now, the worry about this at the time, from the NASA perspective, was that the source of it would be the space shuttle. And so there was a lot of consternation at NASA that maybe the space shuttle would deplete ozone. Well, that was pretty quickly followed by this paper, the Stratospheric Sink for Chloromethanes, by Mario Molina and Sherry Rowland. And they showed that, in fact, these CFCs accumulating in our atmosphere, their primary sink was the upper stratosphere, and they would release chlorine, and that would catalytically destroy ozone. So you've got a big confluence of factors here. People are worried about the SST. People are worried about chlorofluorocarbons. They're worried about the shuttle. So there's a whole bunch of things occurring back in, this is in 1974. But Congress actually did something about it. So what they did is in 1975, they held hearings in the 94th Congress, and they decided to initiate and carry out a program of research, technology monitoring, and other appropriate activities. And in the Clean Air Act, they actually mandated NASA to do that. So in NASA's charter now, that 1958 charter under Title IV, NASA is actually chartered to look at atmospheric ozone. In fact, they do a boundary, though. They said above the tropopause in the act. So we're actually mandated to do the stratosphere and the mesosphere and the thermosphere, but we're not mandated to do the troposphere. But science moves on no matter what. So the first thing, one of the first things they did is they created a report. This is a report that was led by Bob Hudson, the Stratosphere, Present, Future. And I show this because there's some projections of what would happen to ozone because of the release of chlorofluorocarbons. So you can see they've got three scenarios. This one numbered 3 here is just a 5% release rate growth per year from 1975, and you're getting up to 30% ozone depletion. Now these were using really simple one-dimensional models. Models are evolving at this time, but they're very, very crude and simple. Yet they're saying that their huge ozone depletion is possible. They're pointing out there's an existential threat here because of these chlorofluorocarbons. So this is one of the first, following the SIOP reports, this is the first big NASA report. So that was kind of followed in 1985 by these 3 gentlemen. This is on the left is Joe Farman, Brian Gardner, and on the right, John Shanklin. They're standing in front of a Dobson spectrophotometer. So Gordon Dobson back here, he actually built the first of the spectrometers. This is taken down over Antarctica, and they're showing this precipitous decline of the total column ozone above Halley Station down at Antarctica. Now, this station was established in Antarctica because of the International Geophysical Year. So all these data are derived because the IGUI was set up, and they continued to measure ozone. Look how critical it finally becomes in the end. Here's the first picture of what we call the ozone hole, and this is why we call it an ozone hole. This very picture. Down here in the bottom right is P.K. Bartia. P.K. used a big room of computers to actually produce this image. This is published first shown in 1985, and I believe it was Mr. Sullivan at the New York Times, Walter Sullivan, who actually kind of coined the term ozone hole because it looked like there'd been a hole punched in the ozone. Here are the BUV instrument data from on Nimbus 4, those 3 points. Here are the Nimbus 7 TOMS instruments in red, and they're exactly showing the same behavior as we're seeing over Halley Bay. Well, that was followed in 1986 by a very large report, 3-volume report. This involved a lot of coffee. You can see the coffee's already gone. And this report actually said it was published, it's atmospheric ozone in 1985, but it was published in late 85, early 86. And it actually talked about the continued release of CFC11, leading to column depletions of 5 to 8%. With different losses in different regions, 4% in the tropic, 14% in the polar regions. Now, this report actually those numbers don't include the ozone hole. So the projections of ozone loss were a lot less than what it actually turned out to be happening. The actual situation in reality was much worse than we had predicted. It's something to keep in mind when we think about climate. People talk about the best projections. It could turn out to be a lot worse than we imagine. Okay, so in 1987, what did the nations do? They negotiated the Montreal Protocol, which regulates the production and consumption of specific substances. These are the chlorofluorocarbons and halons. It was ratified by the US Senate in '88 and signed by President Reagan shortly after that. And the Montreal Protocol is now signed by the Vienna Convention that predates the Montreal Protocol. The Vienna Convention actually called out ozone depletion as an issue of world concern. Then the Montreal Protocol was signed. It's now both conventions, the Vienna Convention and the Montreal Protocol, signed by every country in the world, everyone, including the Catholic Church, the Vatican, has signed it. And then we bring it to the next thing, which was in 1995. Right here, there's Paul Crutzen, Mario Molina, and Sherry Rowland were given the Nobel Prize for their work in atmospheric chemistry. So not only the nations of the world act, but in fact, the Nobel Laureate Committee recognized these 3 individuals, and there are a lot of other people who are called out in that particular report for the work that they had done. Okay, so now sort of starting to get to the present. This shows a long line of satellites that have been measuring ozone. And Nimbus 4, the OGOs, the Nimbus 4, Nimbus 7 are not on here because this is a plot I got from Rich McPeters. He starts it up here in the late 1980s, so some of the earlier satellites aren't on here. But we've had a nice, long, continuous record of measuring ozone. And I'll show you in a minute that we're going to continue to do that. So the present. The first thing I'll tell you about is that Dave Fahey will be giving a talk about the latest assessment of ozone depletion tomorrow, Wednesday, bright and early, 151B, which is over in the other building. So please come and see that if you want to see some of the newest findings. I'm going to come back to some of these assessments. Everybody has seen the IPCC reports. Sort of the grandfather of the IPCC reports is back here. I showed this one already, but we've been doing every 4 years, we do a new report. Here's the one that'll be coming out, I think at the end of the month or maybe next couple of weeks of January. These assessments are really a key thing that has happened in science. These are peer-reviewed literature. They're based on peer-reviewed literature, and they're extensively peer-reviewed themselves. They're designed to bring science to policymakers. They're international in atmospheric composition, or in author composition. So countries can't reject the findings of the United States scientists, and vice versa. We have our European colleagues, our Asian colleagues, people from around the world work on these. And actually, science speaks with one voice. We say, well, this will happen, we believe this will happen, and we're not certain about these other things. But it allows us to say where the uncertainties are and where we think things are going. Now I'm going to talk a little bit more about these chlorofluorocarbons. And here's a nice sand diagram, and this shows this thing called EESC, really is an indicator of a combined stratospheric and combined CFCs and other ozone-depleting substances like carbon tetrachloride here. Here's methyl bromide, methyl chloride. These are natural compounds. So you can see in the 60s and 70s, ozone was going up, and the Montreal Protocol was signed, and things have been slowly coming down. So here's CFC11. This is the thing that Jim Lovelock measured. CFC12, it's co-produced with CFC11. Carbon tetrachloride, that's the feedstock for both of those gases. And there are a bunch of other CFCs. The reason things have fallen off pretty quickly is actually because methylchloroform only has a lifetime of about 5 years. So it's been coming down fairly quickly. So things are on the mend as far as the ODSs go. Well, let's go to a movie about this year's ozone hole. So this is this year's ozone hole. This is put together with the GMAO does a data assimilation of MLS data and OMPS data, and then we could put together in a nice every 3 hours. So Eric Nash helped produce the movie. You can see the formation of the ozone hole. Things are really deep. Here's the ozone scale, low ozone in purple. So there's the ozone hole for this year. You can see the date. And you can see it reaches full depletion at about 18 kilometers. It's 100% depletion. As you get into November, you can see things begin to break up, and you mix out all this depleted ozone. Ozone gets lowered across the planet. So this is the 2018 Antarctic ozone hole. So the ozone hole is going to be with us, and it's because the chlorofluorocarbons have very long lifetimes. CFC11 has a lifetime of about 55 years. 12 is a lifetime of over 100 years. So I guarantee that for the next couple of decades, you're going to be hearing about ozone holes. Now, just to give you an idea of the ozone hole and where it's headed, this is year down here at the bottom. This is the size of the ozone hole over here in million square kilometers. The green line here shows the size of the North American continent. And so you can see that there's, so here the ozone hole was virtually zero back in '79. And it got up here into the 20 million square kilometer size. And you can see there's the gray bars just show it's all the daily values. So it's the range of values over this 7 to 13 October period when the ozone hole hits its peak. And 2002 was a very interesting dynamical year. This is the 1 year that there was a major stratospheric warming down over the Antarctic. They're common every couple of about 3 years in the northern hemisphere, we have a major stratospheric warming. They don't occur, we didn't think they occurred in the southern hemisphere until the year 2002 came along. It warmed things up, made the ozone hole a lot smaller. But I think if you kind of remove that particular point, that you can see that things are starting to drift downward. It's, we're no longer up here in these high 20, nearly to 30 million square kilometers. You can see a slow downward drift. So that's good news. Chlorofluorocarbons are declining, and it now looks like the ozone hole is starting to show some signs of improvement. In the upper stratosphere, this is from profiles in the northern hemisphere mid-latitudes. This is 79 to 97. This is when chlorine hit about its peak. So here's the trend, and you can see ozone is declining in the stratosphere. So that's what that says. If you go to the present and you just choose the last 13 years, this is from the previous assessment. Dave tomorrow will show the newest graph that includes more years. But here you can see from 2000 to 2013, you can see evidence for an increase. And it turns out if you model this, you can model it pretty well. You can show about half of that increase is due to this red line here from the model. It's due to decreasing ODSs, and the other half is from increasing greenhouse gases. So CO2 acts to actually cool the stratosphere off, which slows the catalytic reactions that deplete ozone. So actually, climate is having an ozone improvement effect. So now I'm going to talk a little bit more about something that I think is really exciting, and it's bringing us to sort of a new, I think stratospheric science is kind of reached what I would call an institutional phase. We're monitoring things, we understand things to some extent, to a large extent, and we're just sort of making measurements and being vigilant. Now we have to start, I think, worried about ozone down a bit lower, and that's where tropomi comes in. And these are some slides that has been given to me by Pepin Vivkin, and this is a plot of his methane plot coming from tropomi. This is about a 45-day period from last year showing methane. Here's another one showing NOx. Pick your favorite spot of the Earth and you can see, or excuse me, not NOx, NO2. You can see various cities on here. You know, you can sort of see the Philadelphia, New York, you can spot Chicago up here, Dallas down there. You go to other places around, you can see Johannesburg down here. There's no real big city here. This is probably a result of biomass burning here. So NO2 from tropomi and formaldehyde from tropomi. Formaldehyde is a key intermediate species in the chemistry of the troposphere. And I'll show you a projection in a second. The next thing I want to show you is kind of the avoided future. There's what would have happened. This is what chlorine we think it'll do. Here is a projection where it's just business as usual. The ODSs, or chlorofluorocarbons, just increased 3% per year. And so we kind of made a movie of that here. So here, that same chlorine line, you'll see it as the date crawls along. You'll see it kind of hit its peak, and one line will start falling this way. That's this world in total ozone. And the other one will start heading up, getting higher and higher. Here's the total of the global column amount. And by the way, this is a simulation that was done by Luke Oman at NASA Goddard. So thank you, Luke. You can see chlorine getting high. You can see the ozone hole in both simulations. This matches pretty well what we truly see. There's a little bit of an offset. But you can see in the world avoided with these higher chlorine levels, you can now see the ozone hole was bigger. As you get out into the 2020s or so, you'll begin to see a pretty good Arctic ozone hole forming. So if we had done nothing and it had continued to go up to 10 or 15, you can see we would have started forming a pretty good Arctic ozone hole every spring. You compare the expected world down here, you can see these high peaks no longer up here in the northern hemisphere. The high columns that you see in the southern mid-latitudes are gone. And as you go along, things just get worse and worse and worse. By the year 2065, at this 3% CFC growth rate, 2/3 of the ozone layer would have been gone. Now, the implications of that, of course, is if you went outside, you'd get a sunburn a lot faster. For me, I get a sunburn fast no matter when I go outside. It's a problem of being a blonde-haired, light-skinned guy. In this world, it probably takes me maybe 15 to 20 minutes to get a perceptible burn in the middle of summer. In this world, it would probably take 3 to 5 minutes for me to get a burn. Cataracts, though, increased UV causes cataracts. That's true for everybody. With 2/3 of the ozone layer gone, probably cataracts would be a lot worse. The worst part of this world, though, is crop yields. Crop yields would go down quite a bit in this world. And you wouldn't be able to feed the planet in this world. So yeah, we could stay inside, in the middle of the day in this world, but your crops can't. So this would have been a pretty bad place to live with food security issues, trying to feed the planet. This would have been a disastrous world to be in. Okay, so I'm going to try to hustle through here because I can see my yellow light. There are a couple of reports that have come out if you want to find out about the future, what we should be doing scientifically. There's this report which was written by this cast of characters down here, The Future of Atmospheric Chemistry. It's a really great report to go read. It's focused mainly, because it was funded by NSF, it's mainly focused not on satellites. So the other report is the 2017 Decadal Survey, and they actually have a couple of atmospheric chemistry missions. There's an aerosol mission under the designated, the Earth System Explorers for greenhouse gases, ozone, and other traces, and there's incubation and venture missions that will probably be written. The future of satellites, there's the entire JPSS series that will be going up in the future. So you can see way out here into the 2020s, there are planned ozone measurement instruments. If you go on from that, just a few speculations here. There's the Decadal Survey implementation. Well, we have an ozone trace gas mission coming out of that. There's a series of geosynchronous chemistry platforms that are planned. Tempo, which is being built, GEMS, which is a Korean satellite, and Sentinel-4, will be in geosynchronous over Europe. There's also a planned Sentinel-5, and I hope that that Sentinel-5 mission will be able to do the same things that TROPE-OMI is currently doing, but at a higher resolution. It really makes a difference in the troposphere to get down to very high resolution if you're going to track emissions backwards. Okay, what about other species? Chlorine, aerosols I think is covered to some extent. Small sats and CubeSats are likely to dominate future observations. The other thing is the commercialization. This is a policy issue, but commercialization of observations. I think we've all come to realize that even your little clicks on your devices that you're using, that's worth money. That gets commercialized. And Earth observations are more and more being commercialized. There's the selling of right now of the GPS occultation measurements, or people are trying to sell them. I think that'll be a trend that we'll see in the future, that in fact more observations will be commercially bought. Where is chlorine headed? We can see chlorine, again, this is the same diagram I showed. It'll hit a peak, and it's going to be dropping off. So the ozone hole recovered some time out here in the 2060s, 2070s. If chlorine behaves like we think it will, that is, the world's countries continue to control them. The ozone hole, where is it headed? Here's a series of images, again, from a model simulation that Luke did. You can see things got bad, but it's improving with time as chlorine goes down in the chlorine and bromine. So that sometime in the 2070s, we should be back to 1980 levels. There's a few problems there. Accountability, will the ozone recovery? That's for us. We told the world that, in fact, ozone depletion would be bad for the world, that we're accountable for those projections. There could be minor accelerations. If they were go and capture, instead of just tearing down buildings, there's foam in these buildings, insulation. A lot of those older buildings have, it's F11 blown foam. If you just destroy it, you release the CFC11. If you try to capture it, you can maybe accelerate a little bit ozone recovery. And there are some species like carbon tetrachloride, which is probably coming from chloromethane plants and chloroethylene plants. It's being inadvertently released. Those things could also be controlled. So there are ways to accelerate things a bit. Greenhouse gases is probably where we really worry a lot. Here are three. These are the representative concentration pathways for CO2, methane, and nitrous oxide. Methane and N2O are source species for nitrogen and hydrogen in the stratosphere. Carbon dioxide is not a source species, but it helps control the temperature. As I mentioned, as carbon dioxide goes up, cools the stratosphere, will accelerate the ozone layer. I think the main point of carbon dioxide is you probably can't go home again. That is, we don't get back. Here's the projection. This is the RCP, I think this is 2.6. It gives you the low levels of greenhouse gases. Here's RCP 8.5. So there's a real scatter in where we think we're going by 2100. Ozone depleting substances are getting better, but the greenhouse gases, we don't know where they're going, and therefore we're not sure where ozone is going in the future because of that. It's certainly going to go higher. So like I said, we don't get back to that pre-industrial ozone world. So as I've already mentioned, as ODSs decline, evolution of ozone is largely controlled by ODSs. So I'm going to skip by that. Talk about surface ozone real quick. This is a plot of surface ozone, and this is in ppb. So you can see the scale here. So 0 down here in purple, 16 up there in red. Mainly, so where you see purple, these are low increases of surface ozone. Where you see red, it's pretty good. Increases up to about 16 parts per billion. This is what we're looking at in sort of the 2090 to 2100 time frame. This is a 10-year average, again, from another simulation that Luc Oman did. So mid-latitude ozone in a future world is probably going up because of greenhouse gases. And this is how, if you increase methane and you keep everything about the same, this is how you take methane and it results in production of formaldehyde and ozone here. So when you look at this, you see why a satellite like TROPE-OMI is important. It measures methane, it measures NO2, it measures formaldehyde, it measures ozone. So in our future world, we need to make measurements of these things. So just a quick summary, and then future climate. I'm going to show this real quick. The Montreal Protocol actually controlled hydrofluorocarbons, HFCs. CFCs are also powerful greenhouse gases, and those are controlled. So those would have been coming down over the years. But they were being replaced with HFCs that have little effect on the ozone layer, but they're climate gases. So they've been controlled under the Montreal Protocol by the Kigali Amendment. And so this is showing the temperature. This is a plot that comes from Gus Velders. You can see this is the business as usual if the Montreal Protocol had done nothing. So the temperature would have increased something like 0.3 to 0.5 degrees because of HFCs. And now you can see it'll be probably, because of the Kigali Amendment, less than 1/10 of a degree. So that's also very positive news about the protocol. I'm going to skip by that, and I'm going to talk just a moment here about uncertainties. So there's still big uncertainties in the future. And compliance is one of the big issues. There is a paper on increases of chlorofluorocarbon-11 production. So we've seen it jump upward in the last few years. I encourage you, if you want to know more about this production of CFC-11, go see Steve Monska's paper. I think that's tomorrow morning, I believe. And then very short-lived substances. There's compounds like dichloromethane that are used as solvents. They've also been increasing. There's rockets and SSTs. As companies like Virgin Atlantic talk about more rocket launches, what's going to happen to the ozone layer. There are companies that are talking about building SSTs again as business jets and small commercial jets. So SSTs are going on. I think one of the biggest uncertainties, and my friend Dave Fahey will go into great detail on this, geoengineering. What are we going to do if we need to do something to cool the planet? Geoengineering will probably have a pretty good impact on the stratosphere and on other things that we may not recognize right now. And then finally, you know, the ozone hole ambushed us back in the mid-'80s. I think we understand the stratosphere pretty darn well now, but I'm not so self-assured to think we've captured everything. And particularly as the planet changes because of climate, we may be ambushed. And I think we have to be prepared for that. So just real quick science summary. I really believe that rocketry, satellites, ozone research really converged to avert what I think would have been an environmental disaster. And I think that everybody in this room, everybody involved with rocket research, satellites, can actually give themselves a round of applause for that. Stratospheric ozone is getting better. It's a huge success. There's also the climate impact of those gases. That's also a success. Tropospheric composition. We hear every day about people dying from pollution events. I think this is the big challenge. Ozone science now is down in the troposphere. And as I've already pointed out, I think we can't just rest on our laurels. We have to continue to do our jobs here. So with that, I want to end with a quote from Piers Sellers. And here's a picture of Piers, who passed away a couple of years ago now. He was surprised that the atmosphere was so thin relative to the size of the Earth. I already mentioned that, and it's really true. He knew it intellectually, but when you're up there in the space station, it's just an onion skin. So with that, thank you.
Okay, thank you very much, Paul. We have a moment for a few questions, if there are some. And as before, please speak up. The room is busy, so questions. Aren't there any atmospheric chemists in the audience? Yes, Dennis.
Dennis. That's an ESA satellite. So I think if you want to learn more, there are a few Tropomi people in the audience. There'll be a couple of talks over the course of the week. It's really a terrific satellite. The resolution is spectacular. Pepin sent me a huge raft of figures, and they're terrific fun to look through because it's much higher resolution. It actually captures well a huge range of these species. Oh, so the time period for Tropomi, it was only launched, what, I think it's about a year and a half ago? 1 year ago. So it's pretty brand new. And there is a replacement, Sentinel-5, and hopefully Sentinel-5 will have better, it'll be an improved version of that. And we can only hope. It's already a spectacular success right now, but hopefully we have something a little bit better. Okay.
Yes, one more question. Please speak up.
Yeah, thanks, Mark, for bringing that up. Tropomi captures the column amount, and what we do is we typically take, we do pretty well in getting the stratospheric profile. Jerry Zimke has worked on this technique. You actually take the stratospheric profile, you add it up, and you subtract that off of the total column to find out how much tropospheric ozone there is. It's really hard to look, you're looking through the ozone layer to try to see what's at the boundary layer. It's a very challenging problem. And I think P.K. Bartia probably give you a chapter and verse on this. But you're right, it's a challenging problem, and we only kind of do it in column amount. I think I saw one last question back there from somebody. Yeah, go ahead. Well, the answer to that is yes. If we see aerosols as an issue, and particularly changing aerosols or impact on aerosols. So if you look in this assessment, you'll find a lot of words written about geoengineering, not in a single chapter, but scattered through. Aerosols is sort of the same thing. It's a little bit scattered through it. There is no chapter specifically dedicated to that. If changes to the aerosol layer became a source of concern, we would write a specific chapter for the policymakers on that. Okay.
All right. For those of you that stayed around, please join me in congratulating and thanking Paul once again.